Initiation into Linear Algebra. The speaker of our today's session is Dr. Arundhati Krishnan. Dr. Arundhati Krishnan is a postdoctoral fellow in the School of Mathematical Science, University College Cork, Ireland. She completed her PhD from Department of Mathematics at IIT Madras, and her works are in the field of operator theory and operator algebra. On the behalf of Department of Mathematics and the organizing committee, I extend a very hearty welcome to you, ma'am. Now, I cordially invite Dr. Varghese Mathusa, the principal of Matoma College, and Dr. Professor Minnie Thomas Miss, head of our Department of Mathematics, to this meeting. Now, I also extend a very warm welcome to all the participants who are joined in this meeting. Okay, now let's start today's session. Over to you, ma'am.
Thank you. Thank you very much for the introduction, and thank you for this opportunity to be a part of this workshop. Am I audible?
Yes, ma'am.
Yes, you are.
Okay, I'll continue. So I'm very happy to be a part of this workshop, especially because it gave me the chance to revise some concepts from linear algebra myself and learn them even better. So I'll start sharing my screen now. Sorry, just one moment. Is the screen visible now?
Yes, it is.
Okay, so now I'll start my presentation. So as you would have already seen, the topic of today, the main topic of today is the Jordan form of a linear operator. So all the lectures you have seen so far have covered many things, including the basics of vector spaces and eigenvalues and eigenvectors. You've also seen the spectral theorem for normal operators on inner product spaces. So continuing this, we'll see today this Jordan form of a linear operator. So one thing I want to say is that yesterday's lecture and many of the things done in yesterday's lecture by Dr. Tiju Cherian are very important for today's talk. So if you have not already seen it, you should go back and watch it so that there is more continuity when you come to this part of the workshop. Okay, so the goal of the lecture is what I'll talk about now. You already saw that the spectral theorem for a normal operator T on a complex in a product space V gives a decomposition of V as some direct sum of eigenspaces. These are all definitions you have seen. And you saw that you get a very nice diagonal form for T. So why did we want diagonalizability? You have already heard it makes many things very easy when the matrix of an operator has some simple form. So if it's diagonal, that's great. That's the best possible case. But in some cases, that's not possible. And then the next thing you hope for is an upper triangular form. So some of these things were mentioned in the previous lectures, especially yesterday's lecture. So what we will show today is that any linear operator T on a complex vector space, so it does not have to be an inner product space or a normal operator, will show that any linear operator has a block diagonal matrix. So I will define what this means. But roughly speaking, it is a matrix where there are blocks on the diagonals, and each of these blocks is upper triangular. So there exists some basis of B, which comes from generalized eigenvectors, such that the matrix of T has this particular form. And what makes this form very nice? You have already seen upper triangularization of a matrix. When you have this kind of block diagonal matrix consisting of upper triangular blocks, what it actually means is that the matrix has even more zeros because of the block form. And you'll see how that looks as I go on. The next thing is we look at refining this result to get what is known as the Jordan form of a linear operator, which will show that each of these upper triangular blocks has an even simpler form. So to be precise, in this upper triangular form of each block, the diagonal elements will be the corresponding eigenvalues for that generalized eigenvector space, and the line above this diagonal will have ones and everything else is zero. So that's a very simple form, and this means you can do, if you're looking at matrix multiplication, for example, it becomes so much simpler, because as we all know, matrix multiplication is not an easy thing in general, right? Even for us, and even when you are doing it via a code. So when you make the matrix as simple as possible with respect to some basis, then it is very nice for such things. So that was just to summarize what we will be covering today. So if you're looking for some keywords and definitions that we will be looking at, here are a few. You have already seen what generalized eigenvectors and generalized eigenspaces are yesterday. I will just go over these definitions quickly again. We'll look at nilpotent operators. We'll define what algebraic multiplicity means. As I mentioned just now, we'll define what a block diagonal matrix is and what a Jordan basis is. So this is the main goal of this lecture. And all this material comes from chapter 8 of Sheldon Axler's book. Now, if time permits, I will go into these things which are in section C, so chapter 8C of Axler's book, where he discusses characteristic polynomial, minimal polynomial, the Cayley-Hamilton theorem, and a few other things. So I think we will have enough time to do this, but let us see. So the main goal will be to arrive at this Jordan decomposition, and if we have time, we'll move on to these other things. So, like I just said, this material is taken from chapter 8 of Sheldon Axler's Linear Algebra Done Right. As others might have mentioned already, it's a very nice book that explains things in a very clear way. So I really feel, as others have said, that we can pick up this book and understand things, and all of us have taken our material from this book. So many thanks to the author for having explained things so clearly. You see any mistakes or typos in these slides, they are my own, so not anybody else's. And thanks to all of you for attending this workshop, even though it is a holiday today. And also, as I said in the beginning, thanks to the organizers for giving me this chance to be a part of this workshop. So the first few slides, I'll spend quite a bit of time just recapping what is already done. One thing I want to say is what Dr. Gayatri Verma said in lecture 2, that even if you do not understand every single thing that happens in the lecture, understand in the sense of knowing every line of the proof, it doesn't matter. The main goal is to take away the main results and to know that if you go back and look at the proof in the book or the notes, you will be able to understand it. So don't worry, when we all saw this material for the first time, we definitely did not understand it the very first go. So it's always nice to recap these things. So I'm just going to recall a few results from lecture 4. So the first thing was to drive in why it is so nice to have an upper triangular form for a matrix. So in the rest of the talk, we'll always be looking at, I've written here a complex vector space, but I should say that sometimes for some results, we need that the vector space is a complex vector space, but often it is okay if the vector space is real or complex. So so here's the first typo. But after this, I think everything else will be specified for that particular result. So in general, if we have a vector space V of dimension n, L of V denotes a set of linear operators on V. This will be consistent throughout the slides. So having established that, let us recall some results from lecture 4, yesterday's lecture. Suppose T is in L of V, it is a linear operator on some vector space V, and suppose its matrix with respect to some basis is upper triangular. That means it has this form, right? So everything below the diagonal is 0, and you have these elements on the diagonal, and some star here. So these could be any entries. Then you saw that T is invertible if and only if lambda j is not equal to 0 for every j. And using this result, you also saw that if you take some linear operator on a vector space T, on a vector space V, and suppose its matrix with respect to some basis is upper triangular, then the eigenvalues of T are precisely the diagonal entries of the matrix T. So this is to again emphasize why our upper triangular matrix is so nice. You already saw this property for diagonal matrices, but it is true even for upper triangular matrices. Okay, so some more recap. This null of S will denote the null space of S for any operator S in L of V. So to recall what is the null space, it is all those vectors in V which get sent to 0 under the linear map S. So one thing to remember is that the 0 vector will always belong to the null space of S for any operator S. And then you saw this theorem which says that the null spaces of powers of an operator, these are increasing as given here. So here is my first typo. Let me correct it right here. Sorry about that. So this should be to the power 0. So this is actually identity. So the null space of T to the power 0, which is identity, is just the set 0, the singleton set 0. And this is contained in the null space of T, which is contained in the null space of T square, and so on and so forth. In general, for any k, the null space of T to the power k minus 1 is contained in the null space of T to the power k. This goes on. So this should be T to the power 0, which is the identity operator. Apologies for that error, but I've changed it now. Then you also saw that if you take T, a linear operator on a vector space V, and M is some non-negative integer such that the null space of T to the power M is equal to the null space of T to the power of M plus 1. So if at some stage in this increasing chain, two of these null spaces become equal, then the theorem you saw says that after that all the null spaces are equal. So the null space of T to the power M is equal to the null space of T to the power M plus 1 is equal to the null space of T to the power M plus 2, and so on and so forth. Let me just make that correction here also. This is null space of T to the power 0. That is what is equal to 0. Okay. And then another theorem that you saw is that null spaces stop growing. Because we are in a finite dimensional vector space, after a certain stage, the null spaces cannot keep growing. So, because the null space of any operator is sitting inside V. So, suppose the dimension of V is n, and T is a linear operator on V, then the null space of T to the power n is equal to the null space of T to the power n plus 1, and so on. And further, you can always decompose V into this direct sum. The null space of T to the power n and the range of T to the power n, where n is the dimension of V. This is not true for every integer j. For example, it's not always true that the null space of T direct sum the range of T is equal to V. But once you take T to the power of the dimension of V, which is n, then you get this direct sum decomposition. Okay, so so far we looked at some properties of the null space, just to recall. And before that, we looked at what happens if you have an upper triangular matrix. When is it invertible? What are its eigenvalues, and so on. So I'm just recapping so far. So now we'll recap. You would have seen this many times now, but I will just go over them again. The definitions of eigenvalues and eigenvectors. So let T be a linear operator on a vector space V, and lambda is some scalar coming from the field F, which can be C or R. Then a non-zero vector V is called an eigenvector of T corresponding to the eigenvalue lambda let me again say that this should be F. Okay, so it can be C or R. It's not wrong to say C, but this is just to be consistent. So you know what an eigenvector is, a non-zero vector V such that T minus lambda I B is 0. So it is called an eigenvector corresponding to the eigenvalue lambda. And if you gather all these eigenvectors together along with the vector 0 and put them together, you get what is known as the eigenspace of T corresponding to the eigenvalue lambda. And this set, the eigenspace corresponding to lambda, is denoted by E lambda T. So you have already seen, and I said earlier, that given a normal operator T on an inner product space V, so it is a vector space with some more structure, and you look at a complex inner product space, you have seen that V can be decomposed into the direct sum of eigenspaces of T, and that there exists an orthonormal basis of B consisting of eigenvectors of T. So you get a set of eigenvectors which actually form an orthonormal basis of V. And with respect to this basis, T has a nice diagonal matrix. So you would have seen this in the third lecture by Dr. K. Somesh. But also yesterday, you have seen examples of linear operators just on a vector space, not an inner product space or a normal operator, which where this operator is not diagonalizable. And you've seen that in fact there, the direct sum of the eigenspaces, this does not span all of B. It sits inside B, but it's not equal to all of B. And this is what leads to the definition of something a bit more general than an eigenvector. This is what is known as a generalized eigenvector. This leads to the definition of generalized eigenvectors. And this again was seen yesterday. So we'll just recap that. Let T be a linear operator on a vector space V. Then a non-zero vector V is called a generalized eigenvector of T if there exists lambda in F and some K in N such that T minus lambda I to the power K acting on V is 0. So if you were just looking at eigenvectors, this K would have to be equal to 1. So that is why this is a more general definition. All you need for this scalar is any K in N such that T minus lambda I to the power K V is 0. And you would have already seen that this lambda will be an eigenvalue. There is no need to separately define what is a generalized eigenvalue because any lambda satisfying this will actually be an eigenvalue. And for these generalized eigenvectors, we collect all of them together along with the vector 0. And what you get is a set which we'll denote by G lambda T. This is called the corresponding generalized eigenspace. Corresponding to the eigenvalue lambda, we write it as G lambda of T, for G for generalized. And just before this, we saw E lambda T, which is just the eigenspace corresponding to an eigenvalue lambda, and that was denoted by E lambda T. Excuse me. So G of lambda T is a subspace of V which contains the eigenspace E lambda T. And further, you saw that this generalized eigenspace can be expressed as the null space of some operator. And what is that operator? It is T minus lambda I to the power N, where N is the dimension of V. Let me add that here. Usually, almost I think everywhere in these slides when I say N, it always means the dimension of V, but let me just write it here anyway. N is the dimension of V. So the generalized eigenspace is equal to the null space of T minus lambda I to the power N. And one more thing, let me go down a bit, you would have seen is that generalized eigenvectors corresponding to distinct eigenvalues are linearly independent. This is also true for eigenvectors corresponding to distinct eigenvalues. That is the first thing you would have seen. But more generally, if you have distinct eigenvalues, then the corresponding generalized eigenvectors are linearly independent. So there is a bit more of a recap, but before that, I just want to ask if, so far I have only been recalling the things that have already been done, but please let me know, am I going too fast? Should I slow down? Am I audible? Anything else that you would like to say?
I have a comment actually.
Okay.
Many people are complaining that they are not able to see the screen. I request all of them to pin the screen, pin the presentation of Arundhati Krishnan from the participants list. Okay, not her video, but the presentation of Arundhati Krishnan. Please pin that.
Sorry, that because I have the presentation open, I'm not able to see the comments or anything else. So, okay, I'll continue. Anyway, all of this material will be made available to you later. So it's okay if you don't have everything written down. And so far, I'm only recapping from yesterday, just so that you again recall what a generalized eigenvector is, because these generalized eigenspaces will be important in the rest of the talk. Okay, so so what we saw is a generalized eigenspace is a subspace of V which contains the eigenspace, because of course every eigenvector is a generalized eigenvector. In particular, this equality is satisfied for k equal to 1. And this subspace, this generalized eigenspace, is nothing but the null space of t minus lambda I to the power of n, where n is a dimension of V. And generalized eigenvectors corresponding to distinct eigenvalues are linearly independent. So I think what we are doing now will be, it is mentioned yesterday, but we'll again look at the definition. So an operator T on a vector space V is called nilpotent if some power of the operator is 0. That is, if t to the power k is equal to 0 for some k in n. So we look at an example of a nilpotent operator. We'll take our V to be this three-dimensional complex vector space, C3, and define n on a vector Z1, Z2, Z3 to be Z2, 0, 0. Then you can check immediately that n is a linear operator. And just consider what is n square, right? Maybe I can just write here. So n of Z1, Z2, Z3 is given here to be Z2, 0, 0. And, okay, I have to select row. So what is n square of Z1, Z2, Z3? Which is equal to n of Z1, Z2, Z3, which is n of Z2, 0, 0, which is equal to, so the Z2 in this vector is 0. So this becomes 0, 0, 0. And this is for all vectors, for all three tuples Z1, Z2, Z3 and C3. So n square is 0. This is an example of a nilpotent operator. So one proposition here is, if you have a nilpotent operator on a vector space and the dimension of V is n as usual, then definitely n to the power of this n will be 0. So that is the proposition. Let's look at the proof. As n is nilpotent, it's given to be nilpotent, there exists some k in n such that n to the power kv is 0 for every v in V, which we can write here as the 0 as 0 acting on the vector V.